to the video, the last in the series in reviewing IB physics. This one will go through both the topic D and topic E, which are very short here, so we'll cover everything all in one go. All right. So without further ado, let's jump right into it. All right. So topic D might be what I personally think is the most abstract of the units here. Okay, but I think this concept still should be fairly familiar to all of you, mainly because that ultimately it is built on these things. It's actually built on our understanding of things prior, okay, about energy and forces, and so well, energy and forces specifically. All right, so let's start with the first one. Okay, well, we always start with gravity. Gravity is very simple, very straightforward, and this is the universal law of gravitation. Right on top, there's a lot of variables here. Okay, right over here. So this is the universal law all right. So universal law of gravitation is basically Newton applying the laws of motion he understood to gravity. Okay, you can understand how objects move. Okay, so G, we call big G, is gravitational constant. And you have two masses. Mass 1, mass 2 are masses. We usually to discuss, to make things simple, we usually think of one mass as a source, okay, the one creating gravity, and one is experiencing gravity. We call that test, okay? But that is completely arbitrary because Newton's third law says every force acts on two objects at the same time. It does not differentiate between them. So the little m, big M, test source is only for our own communication purposes. Okay, so little m is usually test. Big M is the source of gravity. Oh. All right, and R is distance from the center of gravity of masses. Distance between center of masses, I should say. All right. So with this in mind, I'll make it a bit smaller. With this in mind, you probably notice that the first formula can actually be written as G mm over R squared. All right, you may see this written as this way, okay, but they're talking about the same thing. All right. Now, the second one uses the exact same notation, but the second one is not talking about universal law of gravitation. Okay, it's talking about something else. All right, this one is that. All right, second one is talking about gravitational field strength. Okay, because gravity changes depending on which mass is experiencing it. All right, the test. We want to know how a source affects its surroundings. We want to look at one of the objects we call source, how it affects the surroundings. So we actually take the average force of gravity. Okay, average force of gravity. Let me actually write it in. This is gravity. The average force of gravity. All right, and per unit mass experienced by there. So it's gravitational. What? What's going on? This is gravitational field strength. Okay, that's what G is. Okay, little g. All right. Now, of course, if you check the units, that is actually equal to that of gravitational acceleration because we newtons per kilogram, which is equal to meters per second squared. Now, before I continue on to electricity, I'm going to jump into the higher level portion of gravity, which is talk about gravitational potential energy and everything about that. All right. The first two are linked together. I will still explain them separately, but the first two are actually very closely linked. The first one is gravitational potential energy. To derive this formula, you do have to use calculus, to use integration, but to keep things simple here, I am just going to say that it's force times distance r. But it's negative. Okay, I'll explain negative too. So this is gravitational potential energy. Gravitational potential energy. Oh, can't spell. Now, unlike the one formalized in the first unit, this one is not the change in potential energy. It is Z potential energy, because this one actually have a reference height. The reference height is infinity. Is when EP is equal to 0. That's the reference height we chose. Alright, and as our understanding, as we get closer and closer to Earth, you actually get more and more kinetic energy, you lose EP. So if you're losing EP from 0, then you're getting a negative number, right? So that is why it is negative. So therefore, EP are all negative. Alright, that's very important. Okay, and if we consider just how much energy it have for a test object, right, or how much potential per test mass, right? We take that, so we take EP over mass, okay, EP mass, all right. So we get a second one. Second one, of course, is called gravitational potential. All right. Gravitational potential, okay, which is basically EP over the test mass. EP over test mass. All right. So properly speaking, the first one should be interpreted. Okay, since we're using the reference height as infinity, the work needed by an applied force. All right, it's loading. Give it a second. All right, mainly because the object want to follow to Earth, right? You want to fall towards Earth. In order to hold it, bring it to a specific location, we have to slow it down by applying a negative force, if you want, right? Negative, you have to do negative work. That's why it's negative. So you can interpret it as a work needed by an applied force to bring a test mass to bring M1, M2 together from infinity to distance r. You can definitely interpret this, and that's usually a definition too, but I like to think of it as interpretation, right? Interpretation, right? So you can interpret the potential energy as in how much work you need to do to put an object from really far away to a specific location, distance, and leave them there, and don't let them move any closer. Okay, that's why you have to do negative work, because they want to come closer, right? You have to push them. Don't want them. You want to do work backwards so they don't fall to each other. Okay, you want to slow them down. So that's why the work is negative. So that's why it's one way to think about it. Okay, and then potential energy will be that per unit mass. So we choose a test mass, we choose a source mass. How much work is required per unit mass to bring it close to distance from mass m? But if we interpret that way, you get this formula down below right here, okay, which is that, okay, EP over m, basically. EP over m. Right? EP over m. All right? To be more careful, because we're doing work, it should really be change in EP over m. Okay, change in EP. So that's why you see change in voltage here, because you can move it up or down the voltage ladder. Okay, I called it voltage already. The potential ladder, you can go make it increase by bringing it further, or decrease it moving closer. You actually calculate the work done between any input moment over here. So work done is equal to m times delta VG. All right. So if you bring it up, okay, you have to do positive work, because you're increasing in potential. Okay, and then you bring it down, you'll be decreasing in potential. So work will be negative when you bring it down. When you bring it up, you'll be positive. All right. So if we graph it out, we do have to do a little bit of graphing here, okay, to explain the next one. Well, not really, I guess. I could just do it mathematically, but I'll do the graph anyway. So if we graph it out, okay, if you graph potential over distance, then the graph will look something like this. negative, and 1 over r, right? Negative. But it'll stop at radius of the planet, of the source, because inside, we don't know what happens inside. Inside it gets really, really complicated. So graph stops here. Then we tell the greatest change, the slope of tangent line over here. We call that is the gravitational field strength. Or rather, the negative change of that, because the field gets stronger once it goes down. So that's where this comes from. Okay, that's the idea. Is basically gravitational field strength is actually basically the change in gravitational potential over distance. Okay, over distance. But of course, as voltage increase, as potential increase, you get further, gravity gets weaker. So that's why the change is negative. And G is always positive as well. So that's why it's negative. So when we go up, G go down. Alright, so that's negative of the change. Alright, it's a negative of the change. So everything from earlier are linked together. Okay, so the things from gravitational field strength and gravitational potential are actually linked together. Alright, I didn't really define what they are, but I will just say this is a edit. I will be careful. At a given point, while here, well, bottom two over here. Oh, it's frozen again. For the bottom two over here, here's change in potential. Okay, change. Both work and field deal with change. Delta Vg is called change in potential, or potential difference. Change. If you go up, okay, if you go further, it's positive. You go closer, it'll be negative. Okay, go positive, negative. Here it's all, so this value is always negative. If you want, this value is always negative, while this change in delta Vg can be positive or negative depending on moving away or moving towards. Okay, so if our delta Vg is increasing, get bigger, less and less negative, then G would get more and more negative, more and more smaller. It wouldn't be negative because they're all positive. You get smaller. So Vg gets bigger, G should get smaller. Okay, which makes sense because the value gets smaller when we take the negative, right? So same thing here for both of them. All right, combining both and conservation of energy, okay, we can actually calculate the escape and orbital velocity. Okay, so define each of them. Okay, escape velocity is the velocity required. Okay, VSESC is equal to speed required in an object, because you have to get kinetic energy to convert to potential, because you get, as you get further and further, EP will increase, but you have to get the EP from somewhere. That will be the input energy, the EK. Okay, so you use conservation of energy to drive this. Okay, speed required, initial kinetic energy comes from, required to bring an object, okay, from distance r to infinity, distance r to infinity, escaped, and stop. When you're infinitely far, you don't have to move anymore. You can go further if you want to, but escape velocity is the minimum amount of speed, right? Minimum speed. So you have to bring to infinity and stop there. Then good, you escaped, that's it. You can have more, you will be safe, you can go further, but the minimum speed required to escape is this value, which means by minimum, I mean bring it to infinity and stop there. So that's minimum. All right. And the bottom one, on the other hand, does not require conservation energy. This one uses circular motion. Okay, this one uses circular motion. Okay, oh, I should add it in here. Uses cons of E. Okay, the bottom one does not. This one is called orbital velocity. Speed. Well, I shouldn't say, they're called velocity, but there's no direction associated. It should be escape speed. Orbital speed, I changed it. This one uses circular motion. Okay, so basically Fg equal to Fc, which is equal to Fac. with that? Basically, it's a speed of an object at an orbit of distance r. To maintain a distance r from the center of M. That's it. Okay, to maintain a distance. If you go any faster, you get any slower. If you go any faster, you'll have more energy than you're supposed to, so you will escape, right? You'll increase the energy, will become potential energy, kinetic energy will convert to potential. Okay, you'll end up going to a higher orbit. All right, higher orbit. So those extra speed, extra kinetic energy will become EP. Or if you're too slow, gravity will pull you in, and then some of EP will convert to EK until you become fast enough in a lower orbit. So you become fast. So you're too slow, you actually fall and become faster and faster until you're fast enough at a different orbit. Or if you're way too slow, you can never get fast enough to be stable. You will just crash. Then your spaceship will explode. All right. So that's what this one is all about. All right. So either if you add speed to this, if you add the orbital speed, you jump to a higher speed. If you lose, you fall to a lower one. But as you get higher, you get slower and slower. As you fall down, you get faster and faster. Once again, that can be explained by energy. So energy is sort of still behind the scenes, if you want. Okay, energy is still behind the scenes. So that's gravity. Okay, that's gravity. Now, the reason I did gravity first is because I can just say electricity is exactly the same thing, and we're moving on. No, I wouldn't do that. But electricity is very, very similar. Okay, electricity is very, very similar. Okay, the formulas are exactly matched up. All right. So this is not universal law of gravitation. This one is called Coulomb's law. Notice I mentioned some variables not used directly. Okay, that's because Coulomb's constant is given to you, but inside Coulomb's constant actually hides the permittivity of free space. Okay, so let's write down here. This one is Coulomb's law. Okay, you notice it's exactly like gravity. I'll still write everything down. K is Coulomb's constant. Q1 and Q2 are charges. And just as before, sometimes we use little q for test and capital Q for source of electric forces. All right? And R is distance from center. I'm not writing it again because it's the same thing. All right, so put it over here. Now, you will notice something quite interesting here. Okay, something quite interesting here is, of course, I have electric field still. So E is electric field. I'm not reformatting it like gravity because they're very similar. However, I introduce electric field and potential difference right away. Okay, right away here. Okay, right away. That's because this is not dealing with. Okay, I'm not dealing with space here. I'm not dealing with not dealing with electric field of a planet. This is electric field strengths between parallel plates. So that's what this one is. I'm going to make this one bigger actually because I'm sharing. All right. This one is actually a little bit different. This is electric field between two parallel plates, which means uniform field. Which means the field here is actually a constant value. Which means if you know the potential difference, okay, V here is actually the potential. It should be categorized as the potential difference. Okay, it should be. I would say we should use delta V here, but like the Alberta curriculum book would done, but they don't. IB doesn't do that. Okay, so I wouldn't use delta, but this one is actually potential difference between the plates. Okay, or 2 points. It can be 2 points or 2 points if IB want to make things interesting between the plate. right? So it can be between two plates, okay, or between two pointed plate, okay. And D is separation of the plates, distance between the plates, or 2 points, depending on what kind of question is being asked. So the key thing about this question is, since you know the field is constant, right? So you can calculate the total field between two plates, and then you can in turn calculate potential difference between any two given points. So I'll draw a picture here. So you have two plates. If we know the voltage difference between the two plates, okay, and distance, you can calculate E between those two. So you can get E from them. However, instead I can ask a further question, follow up. Well, if I know the voltage here is this, let's say like this 5 volts. What about here? Question mark. Right? What about over here? Then, because the field between them is the same, you can use a new D and calculate the potential difference between those 2 points, and you have to know which plate is positive, which one's negative. If you're moving toward the positive plate, voltage potential increases, negative plate, potential decreases. So you don't have to do that, but at least you know the potential difference, and you can add that to 5 to find the potential at the second point. So that's what they would do here. That's the kind of question you could use the second formula here for, which is you know the total field from a plate and distance between the plates. Then you can figure out the potential difference between any two given point in the middle because the field is constant. Okay, before the field is constant. And of course, you can also do kind of projectile motion stuff with that as well. And of course, we'll do the higher level version of the same thing. However, I don't think I will need to explain too much other than basically everything works exactly the same. Okay, bursts work exactly the same. The only difference, okay, I should say same as gravity. Okay. Similar to gravity. The only difference is because unlike gravity, there are two charges. And gravity, if anything, there are two negative charges, right? That only pulls everything in, right? Everything's attractive. While for electricity, you can both repel and attract. That's why the negative sign disappears. See, there's no negative sign here. The reason there's no negative sign is because everything is defined based on the positive charge, which repels each other, which repel from positive charge. No negative sign because defined as between positive and positive charges, which repel, which means EP actually decrease to a 0 and infinity for a positive charge, right? So the negative would actually come if it turns out one of the charges is negative, let's say Q1 is negative, Q2 is positive, then EP ends up being a negative number, just like gravity, once attractive, right? So it's repulsive force, EP decreases. Okay, EP decreases if further. Oh, or another line, EP decreases if further. And if Q is negative, and if Q is negative, then the charge would be, then the force become attractive. And EP and V become negative again. EP and VE will be negative. Which once again, just like gravity, right? Once attractive. Gravity is always attractive, so everything's negative. So if a source is positive, Q is positive, for instance, right? Or Q is negative. Okay, Q is negative, then a positive charge, test charge, will be attracted to it. So positive test, yeah, positive. For positive test charge, repulsive force. Okay, So yeah, if a source is negative, you'll become attractive. You'll behave exactly like gravity. However, we still want to make sure that electric field, okay, direction of the field is greatest change. So we still define the field to be negative change in potential, okay, because positive charge move in the direction of the field, right? So the potential, as you move, basically you move opposite direction, you always move in decreasing potentials if you want. Okay, so E is still this. Okay, still E is still negative delta E over R. Okay, and then work, of course, doesn't change at all. That all is taken directly from gravity, except mass changes to charge. All right. So I will not go through the explanation of how this formula work again because they're exactly the same as gravity. You can rewind and watch that if you want. Okay, but otherwise work exactly the same as gravity. I can say that. Okay. Otherwise, how it works is exactly the same as gravity. Okay, same graph. Oh, actually, almost same graph. There's one more thing I will say. It's the only difference. It's not the graph. It's no longer stops at the radius. The graph actually, for negative charge, actually goes all the way. Oh, frozen. Can handle the artistic talent of me. Just give me a second for this to respond. All right. So negative charge will actually look like that. So negative charge. Okay, this is B and this is R. Positive charge will look like that. So that's why when you go online, look at electric field, you see those mountain stuff, right? You see something like a mountain and a valley. You see electric field draw like that. That's what that's this. That's a VT graph, VR graph. So you have a positive charge here, positive source, and negative source over here. And they represent the potential energy using that because it's very visual. Because gravity, high potential energy means high for the tall, low potential energy means low. So we sort of imagine it like, oh, really a lot of potential. It's really high here, really low here. So the ball would roll this way. So a positive charge will roll down the hill this way. So that's how it will move. So, but that's not what it actually looks like. It's an approximation of this graph. It's just a really visual way to understand why charges move from positive to negative. It moves this way, and it gets fast, and it's really fast here, slows down, and speeds up again. Why did it do that? Well, this is why, right? So it's why you see that. All right. So that gets a graph. It's something different, not that different. All right. Finally, not finally. There are two things. So we'll have to do another unit. Almost finally. D.3 is about magnets. Okay, magnets are really fun. Okay, these are basically talking about the hand rules you learned, first, second hand, Ampere's law, and the loop law, which is the old derivation of Ampere's law, and finally the third one is the name I cannot quite remember, but the hand rule. Is it Lorentz? I want to say Lorentz. I can look it up on my cheat. I did not write that down on my cheat sheet because it's not that important, so I don't think I find it. But I'll still look it up anyway. But basically, it's the hand rules, okay, and how we determine the direction of a magnetic field around a moving charge. Now, only one of them has a direction, has a formula, because that one actually requires you to calculate. Okay, it requires you to calculate. Okay, I'm just a quick look. Ampere's law. Faraday's law is the next one. Well, Faraday did discover it. Fleming's. There we go. Fleming's hand rules. All right, Fleming's hand rule. There we go. Fleming's hand rule. So, I think I should not box the third one here. There we go. All right. So let me explain what all these formulas are talking about over here. So F is the magnetic force. All right. And magnetic force generated, okay, for these formulas, remember what happened in Ampere's law. Okay, Ampere's law is when you have a moving charge, it generates a magnetic field in the direction of perpendicular to it, which is a loop around the wire, a loop around its motion. All right, that's Ampere's law, or the first hand rule. Okay. But here is what happened is if you have a moving charge creating its magnetic field, and it interacts with an external magnetic field, okay, one that's outside. So there's going to be a force exerted between the charge and the object, all right, and then a magnetic force is calculated using the formula. Q is a charge that's moving, right, and V is the speed of the charge, all right. Now, if we can imagine the charge is moving at a certain speed, or we can also imagine, okay, it instead of a charge moving at a certain speed, we can think of a charge moving, a current moving a certain length, existing with a certain length. That's exactly the same thing, right? Exactly the same thing, because current is just how much charging flowing per second. So you can also imagine it as current flowing through a specific length of wire. In the field. So you can act on a charge over, you can act a moving charge over moving at a certain speed, or you can act on a certain current at a given length. The first one is usually used when we're dealing with a single particle or a few number of particles. We know its speed, we can control its speed and how it moves. While the second one is more like a piece of wire. We don't know how many charges moving in there, but we can measure the current using an ammeter or something else. But they're actually the same thing. But all it comes down to is they're both under the influence of an external magnetic field. Okay, everything's under influence on the magnetic field. It's very important to know that, okay, that the direction of the wire, the force, and the magnetic field are all perpendicular to each other. So I'm going to write this on the side here. I want to put in a note that the magnetic force, and the magnetic field, external, exerting the force, and the direction the charge is moving. So you can say that's a length, or you can say it's speed. Okay, they must be perpendicular to each other. That's why you need three fingers, each pointing in a different direction. All right, that's the first one. That's basically how magnetic field affects the wire, which are moving charge inside. All right, the most interesting question is about mass spectrometer, which causes circular motion because the force is always perpendicular to its movement. So this will result in the particle moving in circular motion, which results in mass spectrometer, and you can use that to determine the mass to charge ratio from there. All right. So the last one is not too much to do with the previous scenario. Here is if you have two wires, right beside each other, both have current passing through it. Then the average force per unit length on that wire, okay, is going to be this formula right here. So I'll write down the variables here. Okay, so force is magnetic force between the wires. Now, length, of course, is segment of the wire that's actually attracting or repelling each other, right? Length is the length of segment. Interacting. I1 and 2 are the current in each wire respectively. Current. And mu0 is the permittivity, not permittivity, permittivity of free space, yes. Permissivity and permittivity of free space. You can find on the formula sheet. All right, formula sheet. All right. I think the most interesting part is you'll notice, unlike the formulas above, magnetic force is not 1 over r squared. Gravity is 1 over r squared, right? Over in G equal m1 m2 over r squared. Electric force is kq1 q2 over r squared. This one might seem similar at the beginning, but it's actually very different. Because magnetic field along a wire is spread out in a circle, not in a sphere. Okay, so it's not r squared, it's r, but it's not inverse square relationship with r. So pay very close attention to that. It might be similar, but it's not quite true. All right, once again, I will not draw it here, but just know that it's not inverse square. All right, last in this lesson, in this topic, okay, we'll have one more left in this chapter, is induction, electromagnetic induction. This is basically summarized by the name of one law, and that law is called Faraday's law. So they're all the same. They all came from Faraday's law. Okay, so I'll write over here. Faraday. Now, this is entirely IB's formula, but the concept is very similar. Basically, if you have a magnetic field, okay, if you have a magnetic field and passes through a loop or a ring, the cross-sectional area, right? Then it has something what we call magnetic flux. So the first one is magnetic. Magnetic flux is basically the total number of magnetic field across in a cross-section. So it's magnetic field times area. Okay, so B is magnetic field, and A is cross-section area. Oh, it's frozen again. Give me a second. Cross-sectional area the field is passing through. Now, we understand that the field is not doing equal amount of work depending on how it passes through. 90 degrees doing the most amount of work, okay, because perpendicular, this one the force is exerted, okay. If it's parallel, then there's no force at all, right? It's because the current will be parallel to the field, there will be no force, right? So area, the field's passing through. Okay, I should do two lines here. All right. So angle here is the angle between the field and perpendicular direction, the normal and the normal. So the angle here is between the field and the normal. So I will draw a quick picture here. So let's say you have a surface that's lying down and the field is passing through like that, right? Maybe I should draw it that way. So you have a surface that's this. Okay, I'll draw a line. What? Faraday's law. Go over here. Think what you did. All right. So this surface, imagine the plane. It's about three-dimensional. Okay, so it goes in and out of the page. Okay, it goes in and out of the page. Then you have your magnetic field lines going this way. They go right through. Okay, right through. All right. Then the normal, of course, is this line right here. I'll draw this one over here. That's a normal line, and the angle right here is zeta. Why we use normal line? It's because normal line is where the force is the greatest. Okay, the force is greatest. Okay, and therefore generate the greatest amount of current. Okay, greatest amount of current. Okay, so that angle is zeta. All right. Then Faraday detected that if there's a changing magnetic field, or if we change the area, okay, changing the area, basically if the magnetic field is moving or the area is moving, or basically if the flux is changing, then the changing flux over time induces a voltage. And of course the voltage is exactly equal to the change in flux over time. Now, there's an n because sometimes you can do loops. So n here, okay, n here, second formula over here, I'll move this one up. Okay, n here, n is the number of loops. Now, the negative is what's really interesting here. It's because it will be interesting because EMF, as we learned from previous unit, is a scalar. So this does not indicate direction here. It's just to indicate, okay, it's just to indicate that the induced EMF always oppose the change. If somehow the flux is increasing and the EMF will be decreasing, if you, in a sense, I think it's trying to make undo the flux change, We call that Lenz's law. So negative just indicate, okay, I was added later on, that basically indicate that the induced EMF will result in a force, that magnetic force that opposes the change in flux. That's it. Okay. So IB is not too strongly tested other than a conceptual level. Okay. Otherwise, just write a negative value there. So basically, if the flux is getting if the flux is increasing, then voltage, the EMF will be increasing in the opposite direction. That's what it's saying, right? You're increasing the opposite direction. Okay, so you're trying to do everything you can to decrease the flux. All right. The last one is basically an application of the formula above, specifically with a EMF induced in a conductor moving in a magnetic field. Okay, so last one here is EMF induced in across the ends of a rod, metal rod, or conductor, a street conductor. Okay, in a magnetic field, and B, of course, is that magnetic field. V is how fast the conductor is moving. Speed of, and L is the length of conductor in the field. Length. Okay, this can be derived by, imagine, basically, you have a magnetic field. Okay, let's say this is a magnetic field going into the page. And you have a conductor of length L inside, and you move it this way. And to imagine how it works is to imagine that this conductor is part of a circuit, and how moving this rod will change that area. Okay, the magnetic field won't change. As you change area, as you know, changing area will change the flux, and then in turn change the induce EMF. Okay, so that's what's going on over here. All right, going over here. All right, and that is unit D. That is unit D. Last unit we'll talk about in the same video is unit E, nuclear and quantum physics. Okay, the most interesting. Okay, I do like circular motion better, but it's only covered a little bit. Okay, but quantum physics definitely I think more interesting as well. Okay, quantum physics is where the formulas is so small, so short. It's because most of the time you're using formulas from above somewhere. Okay, it could be about how fast particle is moving, right? So it's going to be about energy. Okay, about energy work, or it's unlikely you'll be using dynamics, kinematics though. They are more, well, circular motion you might use because particles in circular motion. All right. It's unlikely you need to use kinematics, dynamics, basics. Momentum you might, but these things are not quite used. Besides those, rotational motion, likely because you're moving in orbits. Okay, relativity, maybe if you're moving near the speed of light. But things like thermodynamics, yes, a little bit. Maybe not by conduction, but more so by like ideal gas law. What happens once a particle moves faster, move slower? When there's nuclear reaction, how much energy is released? How will it cause the gas to expand? Basically, my point is, it's usually used in conjunction with something else. Maybe not circuits. Light, definitely. Okay, light and waves, definitely, because wave-particle duality. Okay, and but the formula it uses most is actually from chapter D, the fields, because we always put in the charged particles we discover in some kind of field and make it do something and see how it behaves. So electric field formula is actually used probably the most in here. Okay, but the point is, The reason there's so few formulas here is because it actually uses all the formulas above it to understand what's going on. Okay, so don't underestimate and think this is an easy chapter to study. Okay, it's much more abstract. There's nothing new here, but the goal is you want to see what you already know and how it fits into this topic. All right, into this topic. So when you study, make sure you become very careful with that. The first one is a very famous formula called Planck-Einstein equation. Alright, this basically solved the UV catastrophe from black body radiation mentioned above. See, already tie in to a previous topic, okay? The black body radiation tie in, okay? It's saying black body radiation from Wien's displacement law always peak at a certain temperature, and observation says it always peaks around infrared or below infrared. But somehow classical theories predict it should be higher. So Planck says, well, maybe you cannot heat something so hot because you can only add energy a certain way. So he made things work, and Einstein explained. Turns out light is quantized. Okay, so energy is the energy of a photon. And since there's only so many different frequency of photon, right? So if you add something, okay, if you add energy to something using low frequency light, you can only add so much energy to it, no matter what, right? Because energy is quantized. So there's only so much energy you can add, and of course that is determined by the frequency and by a scaling factor called Planck's constant, because he derived it. Right? So that is the foundation of quantum mechanics, quantum physics. The foundation that energy is quantized. All right? Now, once I understand energy is quantized, we then can, once with that happening, there are numerous studies using that idea to study the behavior of an atom. From Dalton's model, J.J. Thomson's model discovered the electron, until Rutherford discovered the nucleus. Okay, discovered nucleus using gold foils. Using the gold foil experiment, he was able to get the gold foil to be the electrons to be faster, well, F particles I should say, faster and faster and faster. And he noticed there seems to be an asymptotic behavior, okay, to how close the F particle can get to the nucleus. So R here is a theoretical radius of an atom. Of course, that depends on the atomic number. And that is the number of protons. All right, and of course, it's the minimum radius. Okay, that is what we call the Fermi radii, R0. Is what we call the Fermi radii. Radius, which is constant, but is theoretical radius of a proton. Hydrogen, basically H equal to 1 hydrogen. All right. Now we know it's only theoretical is because we learned that we know that protons are actually just like electrons. They are actually quantized. They're actually quantized, which means they're not quantized. They're waves, which means its location is probabilistic. So we don't know if it's just that's a radius of a proton, or that's just the most likely radius of the wave function of the neutron. So proton. So it does get a little bit interesting, but which is called a Fermi radius. Basically, it's the smallest radius an atom can be. Basically, all right. And after Rutherford have some issues with leaking of energy due to Maxwell's equations. Bohr solved that, okay, using quantum model. So this is Bohr's energy levels for hydrogen. Okay, it's best to interpret these as the kinetic energy of the hydrogen. Okay, but it's probably just think of it as, if we look at an actual derivation, it's actually the total energy of an electron, kinetic and potential, but it's definitely proportional to its kinetic energy. All right. So for hydrogen ion, nucleus, no nucleus, atom. All right. Now, it's very important to know that E here is just the energy level. E is energy of the electron. And N here is the orbit number. Or the quantum number of the energy level. The principal, the first energy level. Okay, first energy level. EV just units there. It's covered. This is 13.6. This is measured in electron volts. Okay. Now, for my class, I actually went through the process of driving exactly where this whole thing come from. Okay, from this whole thing come from. You're not required to replicate the derivation Bohr has done, but familiarity with how it's done is very important. That's because Bohr's first postulate is right below. This is Bohr's first postulate. It says angular momentum, MVR, of an electrons are quantized. Alright, so, what did I do there? Oh, that's cool. What? Oh, wait, I don't know what just happened, but that looks cool. Angular momentum, MBR, is quantized for electrons. And therefore, energy is also quantized, right? Energy is also quantized for that reason. Here, m is the mass of the electron. All right. V is its speed. It's moving at tangential speed, is orbit. All right, and r is the orbital radius. N and H already know. N is 1, 2, 3, 4. N is 0, 0, 1, 2, 3, etc. Turns out corresponding to the orbitals. Okay, N in fact cannot be 0 because of the Planck's problem. It cannot be 0. It can only be 1, 2, 3, or 4. It cannot be 0. You cannot have angular momentum of 0. Okay, and because that it actually does cause some problems. Okay, some problems. Yeah, so that is first postulate, which can be used to drive the formula right above it. Okay, formula right above it. Will be a box. Might as well. Do I need a box then? No. All right. So after Bohr's model, Bohr basically opened a door for something very interesting. Okay, which is E.2 quantum physics. Okay. Quantum physics. First, Einstein first come up with to verify Planck's idea using the photoelectric effect formula. Okay, so this is the photoelectric effect. Okay, a classical experiment that predicts how it behaves. I'll write all the formula. I'll write all the variables over to the right here, though. So, Emax is the maximum kinetic energy of emitted photons, electrons. I mean. Remember, Einstein's idea is no matter how much, if your frequency is too low, no matter how much light you shoot at it, no electrons will come out. But if the frequency is high enough, you get electrons right away, and EK is proportional to how much frequency you have. That's what HF is. HF is energy of the photon, as we saw above, right? Energy of the photon. Okay, so the phi at the end, big phi, that's what we call work function. And that is the minimum energy you need to get the electron shoot off. Okay, so that's what the first one is all about. This one is very familiar. I think on the Alberta curriculum they use W for work function, but work is mentioned quite a bit, okay, in this unit as well because of energy, okay, electric potential energy. So we use phi here to separate work function and actual work done by a force. All right. So this is photoelectric effect, indicating the photoelectric effect, kinetic energy of the electron dependent on the frequency and not the intensity. If this is true, then the idea Einstein trying to say that light is quantized does show it, because if you don't have enough energy, because you can only add energy one chunk at a time, right? You'll never have enough energy. You will never be enough to shoot the photons out. But if you have enough, one electrons requires one photon, so you can actually control how much electrons coming out by intensity and how fast electrons come out by frequency. All right. So from there, okay, he was able to prove that his experiment got verified by Robert Millikan. Just remember, Robert Millikan tried to prove him wrong, but ended up proving him right. And Yi max is calculated indirectly using stopping voltage and everything else. The second one is wave-particle duality, okay, which indicates that a wave actually also has momentum. Okay, wave also has momentum. Okay, so it's just the momentum was very, very small depending on the wave itself. All right. So this is first introduced for light. Okay, first introduced light for Compton scattering, but later taken away by de Broglie to understand that particles like electrons should also have wavelengths. So lambda here is what we call, well, for light it's a real wavelength, okay, but for most particles it's the de Broglie wavelengths. For light, de Broglie wavelengths, it's real wavelength basically. H is Planck's constant, and P here is the momentum of the wave/particle. What it indicates is that particles can behave like waves. Particles have wave-like properties, and waves have particle-like properties. So this is the wave-particle duality formula in a sense, right? It's not the only one, but this one that sort of links them together and what's used quite often to understand how things works. Just know de Broglie actually used this idea to explain why electrons have certain levels, and resulting in a very interesting de Broglie's postulate in saying that, as a matter of fact, okay, the only wavelengths that can exist in an atom has to be 2 pi r. And if we understand, okay, and with this he was able to rederive Bohr's first postulate, okay, and then measure, experimentally determine, okay, not experimentally, mathematically redetermine everything Bohr have done. So this explains that. Okay, this explains that. All right, this explains that. Okay. So, of course, Bohr's model, de Broglie's model only worked for hydrogen. Okay, so this model needs to be improved upon by the quantum cloud model, which is you only need to understand conceptually. You are not expected to solve Schrodinger's equation even for only hydrogen. Okay, which is the most solved one. Last but not least is Compton scattering. Compton scattering is another evidence for the quantum property of light. Okay, this is scattering formula. Okay, this is scattering formula. So lambda here is wavelengths before and after scattering. Once again, if waves have momentum and wave has momentum, they should be able to hit a particle and cause change trajectory, and Compton detect that. All right, and that's equal to ME here is the mass of electron, or if IB exam or your teacher, me, decided to give you a trick question and say, oh, you hit a proton, it's a mass that's called scattered particle. Usually has mass though. So electron, proton, not a quark. You cannot isolate a quark, but it will be something like electron, proton, or something small. All right. C speed of light, and the angle is the scatter angle of the photon. Okay, I should say wavelengths of the photon. Oh, take a moment to respond once again. Now, this cannot be explained by classic theory, but remember what I said when we were reviewing waves earlier? Well, not earlier, but in the video, in an earlier video, okay, I said the frequency doesn't actually change. Frequency cannot change. That's what the classic model says. The frequency cannot change no matter what. Frequency and wavelengths cannot actually change. The only thing changing is the speed. Okay, the only way to change is speed. But speed didn't change here. Still speed of light. So the wavelengths will change frequency. That's the only way to change, which is impossible in a classic model. In a classical model. So this is a quantum model explaining what's going on. All right. So that's Compton scattering. I should publish the name. Compton scattering. All right. That is E.2. And that sort of wrap up all the electron models. Okay. And then jump into nuclear physics. So E.3 and above. We'll come back to E.3 down below as well. E.3 talks about radioactive decay and talk about binding energy and what binds electrons together, and that is, of course, the binding energy, which is Einstein's energy mass equivalence. So energy mass equivalence. M is the mass of mass change during a nuclear reaction. Okay, mass lost. Okay, mass loss. Okay, during a nuclear reaction. Okay, it's always bigger. All spontaneous nuclear reaction will always result in a mass loss. So mass always goes from high to low in a spontaneous reaction. And that energy is actually converted to EK. So mass is actually the potential energy inside the nucleus, inside a nucleon, I should say, inside a nucleon, and the energy is lost, not lost, converted to EK, therefore forming a new bond when you lose those energy. So E is the energy released during a nuclear reaction. Once again, you'll be EK because mass lost, mass is actually EP. And released energy is EK. EK usually come in the form of gamma radiation, vibration of electrons, thermal energy of some sort. So that's how kinetic energy is being released. It's converted to a different form of kinetic energy that we actually can experience in some different forms. All right. And E.3, of course, has more IB stuff. These are dealing with half-life and decay. These are the, I'll write them all actually. This is all tied together. Okay, talking about radioactive, we can talk about how fast the radioactive decay happened, or model its behavior. Okay, model its behavior. So, N here is the amount of substance left. Okay. N0 is the initial amount. E here is not a variable. E here is a constant, 2.7 something. And lambda here, be careful, not wavelengths, because seeing a lot of wavelengths here. Lambda here is what we call decay constant. Okay, decay constant. All right, and time passed. Now, you notice, A here is actually the activity rate. So how much reaction happens? We can actually measure these. Okay, we can measure the final amount, we can measure the final amount, right? We can measure the activity rate, okay? And you notice that's equal to lambda n, which means if we know how much reaction is happening, the rate, okay, we can also calculate exactly what decay constant is. If we know decay constant, we know the current amount, we can actually calculate the initial amount, okay, expected initial amount, or we can calculate time. So by measuring activity rate and the current amount, we can actually use that to date substances. Okay, by measuring activity rate and the current amount, we can find the ratio, the decay constant, and using the decay constant, we can backtrack, okay, to see how long ago you'll have the amount we expect to have if it's alive. All right, if it's alive, so we can actually use that to date, okay, past substances, date objects. That's called radiometric dating. Okay, radiometric dating. The last one is half-life. Usually we don't give you a decay constant. Usually things are measured in half-life because half-life is easier to measure. Okay, easier to measure. So if we give you half-life instead, then we can just take the ln of 2 divided by the decay constant to get half-life. T1 half is called half-life. All right, this all done with the hard work of Lady Marie Curie and her husband. All right, so there are many stories, but I just want this one is the one top of my head is because both of them basically died from it. From you know what you get when you're working with radioactive substance all day, every day, right? So sacrifice their lives. All right. E.4 is not on here. That's because E.4 is about nuclear fission and balancing decay equations. Okay, balancing decay equations. Just remember the numerator, the number on top. This could be numerator. The number of nucleons must be balanced. The number of protons must be balanced. That's a conservation of nucleons and conservation of charge. Just make sure those are balanced. Then it's all okay. There's no formulas involved other than maybe you have to once something's decayed, you have to predict. You have to predict whether it's a positive particle, negative particle, and what happens when you pass through a magnetic field, which means you use a prior formula you already learned. And there is very little actual formula to calculate. Once again, it's just about balancing equations. All right. The last one, E.5 over here. Okay, E.5 over here also have very few formulas. Okay. That's because it's also almost entirely conceptual, okay, because this one deals with fusion, which is balancing fusion formulas, which all you have to do is balance the number of nucleons and number of protons, all right? But the thing here is to recognize in the last lesson is you need to know the general process of fusion, okay? That's why it's just opposite fusion. That's pretty simple. And you are expected to understand, okay, how stars look and how its brightness spreads. However, that's not from this unit. How bright something is, right? Brightness or intensity, that comes from way back up. Is it here? No. Way back up, black body radiation. Right here, B equal to L over 4 pi d squared, and of course L is equal to the sigma at to the fourth, right? So you can see how the relationship between those two is. And so by understanding the relationship between intensity and surface area, you can actually get a graph, okay, called the HR diagram, okay, the Hertzspringer-Russell diagram, okay, Russell diagram. You have a rough idea how to read it or how to interpret it. There's some trends on there for stars that we've discovered. Okay, stars that we've discovered. You can study some trends about it qualitatively, and mathematically it's just this, okay, it's all in unit B, mathematically maybe, unit B, so no new formulas. Okay, and that's the main part of that lesson. Okay, and by understanding, okay, how to read a graph, you can now estimate how each star would evolve. For instance, which planet will become a white dwarf when it dies, which ones will become supernova. Okay, which ones are considered sun-like, stuff like that, so on and so forth. All right, the only formula used is how do you determine the distance of distance from a very distant star. So what they do is using this formula right here. Okay, that's the only formula. Now, distance is measured in parsecs. Okay, I'll explain why. Okay, shortly. Distance measured in parsecs. All right, let me see here. Oh not box this one. D is distance to a star. A star or celestial body you observe. And P is what we call parallax. Okay, parallax angle. Okay, parallax angle. RA, LLAX, I think. What? What's going on? Which is measured in, it's usually measured in arc seconds. Okay. P equals P. There we go. All right, measured in arc seconds because how small it is. What's going on? Okay, I'm going to zoom in here. What's going on is, suppose you have a star that's like way over here. All right, and you have Earth. So to know where the Earth is, we cannot measure directly. It's not like we can shoot like a rocket over there and see how long it takes or anything, right? So what we do is we have the sun right here. This is sun, and the Earth orbits around the sun, right? I'll draw a circle around it. Earth orbits around the sun. So Earth is over here. Earth's over here. All right. Now, let's say here it's summer. The bottom is in the winter. Then, if you measure the distance between the Earth, not to measure the angle, right? If you draw a line between the star and the Earth. Oh, something not working here. What? Draw this way. If you measure, okay, it didn't draw perfectly. If you actually measure the position of the star, it actually differs by a little bit, right? Now, the distance between Earth and the Sun is exactly 1 AU. So distance between these 2 points are 2 AU. 2 astronomical units between the position of Earth, between summer and winter. So that's why distance is measured in AU, because we're using trigonometry using AU over here. No, AU. Parsecs. The formula actually uses parsecs. So we have to, okay, so you actually have to convert that to parsecs here. That is okay. Oh, because you convert to arc seconds. I see. Okay. So the units are measured in arc seconds, but the angle is measured in arc seconds. But if we do that conversion, it actually give you the angle measured in parsec, because parsec is actually just a scaled version, okay, of AU. And of course, it's measured by its parsec. It's based on arc seconds. So what they do is they notice that there is a small parallax. There's a small angle in between here and here. We know the distance between here. So the parallax angle is exactly this much right here. This is parallax angle. So that's how much. So from winter and summer, where the star appears in the sky changes by this small angle right here. Okay, by the small angle right here. If we take that angle divided by 2 and measure the distance from here to here, of course this is perpendicular to each other. So we can then use trigonometry to figure out R, because this we know, this angle we know. So we can use trigonometry to find that. Now we assume the angle is really small, really small. So we're using sine. Sine basically is a distance, right? Sine of the angle is equal to the angle itself. So that's why we just get that value instead. All right. So that's why this formula works. And that is the whole data booklet. I'm trying to zoom out so it kind of looks cool. There we go. Zoom out more. There we go. And that is the whole data booklet commented. All right. Congratulations, you went through the entire data booklet with me, and that is the whole video series. Thank you for tuning in, and hope I see you next time on a different physics topic.